what would the mean and standard error of the sampling distribution be? Okay, so we don't want to write down all sets of 5, find the average of those 5 and type them on a list. That was a whole lot of work that we don't need to do. What's the shortcut going to be for this? What do I have to do? Yes, you're going to find the mean and standard deviation of the 0 through 9. So the 0 through 9, we want the mean and standard deviation. Once we know those two, it's a very much a shortcut to get to the other two. So how do I get the mean and standard deviation of 0 through 9? 1 bar stack. We'll put them in a list. Bar stat. Anybody match mine before I write them down?
Yeah.
4.5 is the mean. Standard deviation, which one? 3.03 or 2.87? 2.87 because that was a population. So now, if I had made the big table, which would take us pages of paper to do, I want the mean of my sampling distribution. What's it going to come out to be? 4.5, exactly the same. The means don't change. My standard error, is it equal to that one? What do I have to do to figure it out? Divide it by square root of 5. Because that's how big my sample size was, 5. That's what the property said. So 2.87 divided by the square root of 5. So the sampling error, standard error, always gets smaller. So about 1.28. All right, all leading up to one of the biggest theorems in statistics, the central limit theorem. And then we're going to end here. Mine took almost a whole page. That's what we have left. You guys make me laugh today. Nobody wants to work today. I don't know. I think it's the weather. I know. Everybody's in a bad mood. Central limit theorem. Okay, there's 2 parts to it. It describes, describes the relationship between a sampling distribution and the population, we'll leave it at that. Yep, and?
No, wait.
Between, the sampling distribution and the population. Oh, that's probably what I said, hey? Between a sampling distribution and the population. Okay, now I got it. Okay, 2 parts to it. First part, if samples of size n, where n is greater than or equal to 30. 30 is a magic number in statistics. I don't know why, somebody proved it. Are drawn, I should say are taken, from any shaped population. The quiz you're going to take today, all of your populations, they have to tell you that they're normally distributed for us to find those probabilities, remember? This is key. If you take more than 30 or taken from any shaped population, the sampling distribution will be normally distributed. So, in a picture, what does this say? If my population's shape, whatever I was measuring, was not normal, okay? Not normal. But we can still find the mean and standard deviation of any distribution, where we have a mean and a standard deviation. If I take samples of size 30 from here, and I keep doing samples of 30 over and over and over again, and then I look at that shape, so I have to take at least 30. What happens? My sampling distribution turns out to be normal. And then I can do all kinds of statistics on it. And what do you think the relationship is between the mean here and the mean here? Exactly the same. So the mean here equals the population mean. So the two means are equal. What do you think the standard deviation here is? That little thing we had before, the population standard deviation divided by the square root of the sample size. Standard error. So we're taking something very ugly and turning it into something nice and normal that we can do statistics with. But I have to take at least 30. Okay, and the second and final part. I'll try and squeeze it in here. I better do a new paper. And the second part of central limit theorem says, if a population is normally distributed, then the sampling distribution is also normally distributed for any sample size. So I don't have to hit that magic number of 30. So there's my normally distributed population. It doesn't matter how big my sample size is, but the bigger the sample size, the smaller my standard deviation gets. So I kind of want to draw it in here so you can see it. So I can take any sample size and I will get a normally distributed graph. My two means will be equal. But what do you think happens to my standard deviation of my sampling distribution? It's going to get smaller. How does it get smaller? This standard deviation is this one divided by the square root of the sample size still. So it's always that standard error. So it's going to get smaller, so it's just going to make it a narrower graph. The bigger the sample, the narrower the graph, the more accurate. So means are the same. Standard deviation has that relationship of divide by the square root of the sample size. Okay, your assignment for after the quiz. I know, welcome to school.
I'd rather go back. It's not,
These are easy.
I just think it's only 4-day week.
Page 230, 1 through 12, 12.
That's it?
Yep,
Yep,
3, 6, and 10. Don't strain yourself. 1 through 12, skip 3, 6, and 10.
Okay, that's how I am.
It's doable.
I'll send you a